So now what we're going to do is some of these fun calculus-based derivations where we're deriving fields due to various uniform and non-uniform, meaning not even charge densities. We're going to derive fields due to a line of charge, a ring of charge, and a disk of charge. And many of these derivations are available on this website right here. If you go there, you may find several of these there. The first one I'd like to do is, what is the field at the origin? In other words, what's the field right here at this point due to a line segment of charge that's uniformly charged with charge Q over length L? So I've also added this L here. On the x-axis, the left end starts at x equals a. So right there is x equals a. And of course the other end is x equals a plus L. I just added the length L to that a. So I'm just going to erase this for now. So what's the field due to that at this origin point here? Now the first thing we want to do is figure out what direction is the field pointing in. So you think, if I put a positive test charge right there, which way would that positive test charge be pushed? Well, all these charges are over here. On the right, it would be pushed to the left. So the field is going to be pointing that way. That's the direction of it. Now all I need is the magnitude. How do I figure out the magnitude? Could I just use kq over r squared? I can't, because each of these little infinitesimal pieces of charge, I'm going to pick a random one right here, an arbitrary piece of charge, dq, that is not the same distance away as all the other little infinitesimal pieces of charge. So this is why I have to integrate, because there's an infinite number of these little tiny dq's, and they're all a different distance away from that. What is the, just to get some other information here, what is the width of this dq? Hint, it's on the x-axis. So I'm going to call it the width of this thing across that way. I'm going to call that dx. That is dx right there. So that's how wide that little dq is, and that's going to come in important later. Another thing we might want to realize is that because it's a uniform charge distribution and it's linearly distributed, that lambda, the linear charge density, is going to be what? Well, Q is the amount of charge and it's distributed over length L. It'll just be Q over L. So that's going to come in very, very handy. So to find out the E field at the origin, that is going to be, I've got to integrate over the entire line of charge. I've got to add up the fields due to all of these dq's. And how many are there? There's an infinite number. That's why I've got to integrate. And that's going to be k dq over r squared. So basically I add up all the fields due to each dq and integrate this way. Just k times dq over r squared is the field due to this dq, and then add up all infinity of those, and that'll lead to the entire field there at the origin. So what I've got to do is I've got to somehow express dq in terms of what I know. And a lot of times that is really the challenge here, to express dq. Well, I know that dq, how could I express that in terms of lambda and the width of it dx? And I'm almost always trying to express dq in terms of space variables, and this is no exception. dq is going to be lambda, the linear charge density, how many coulombs per meter, times, well, how many meters wide is this? It's just dx wide. So this becomes, our E field is going to equal the integral, and how do I do this over the entire line of charge? X equals what to what? I'm going to start, the very least x's is a. Notice that here's where I start, x is a, and then I'm going to go to x is equal to a plus L. That's the final x value over here. K, lambda dx, that's dq right there. But instead of r squared, what is my r? I need to have these variables consistent. How far is this away from that point? What is the center distance between the origin and all these different dq's? Well, that's just going to be my x variable. So this becomes x squared. The distance away from the origin is just x. So there we go. I just got to integrate that. And I'm going to simplify this one more time. That's going to give me the integral of from a to a plus L of k times lambda is q over L times dx over x squared. So what I'm going to do is I'm going to take out everything that is not a constant here, or everything that is a constant, I'll take it out. That gives me E equals, I can bring out K, I can bring out the total charge Q, I can bring out the length L, and all that I'm left with is the integral from a to a plus L of dx, or 1 over x squared dx. There we go. So what I get when I integrate that is kq over L times, here's what my integral is going to be. It's, you add, that's x to the negative 2, you add 1 and divide by negative 1. So that gives us x to the negative 1, or negative 1 over x. And I evaluate that from a to a plus L. There we go. And almost done now. That becomes kq over L times, you do final minus initial, so that'll be negative 1 over a plus L minus negative 1 over a. And when you're all done with this thing, kq over L, and then this will be times negative 1 over a plus L plus 1 over a. And there probably is a way to simplify that one more step. The common denominator between these two is going to be a times a plus L. So let's just make that, getting the common denominator like that, we can see this is going to become kq over L. And notice that this will give us negative a, and this will give us a plus L, and this will all be over a times a plus L. So that cancels that. Notice that what's left here on top here is L. That cancels, and our final result is kq over a times a plus L. Now there's an interesting result from this that we can check it when the length of this thing is 0. If it's a point charge, what do we get? If L was 0, this reduces to kq over a squared, just Coulomb's law. So we did it right. That's at least a check on it. So now let's go on to the next one.